Hey everybody, how we doing? Everybody can hear me okay? I can stand like this and it's all good. Thank you. I appreciate the person in the middle there with thumbs up. It's very helpful. All right. My name is Josh Wills. I am the Director of Data Science at Cloudera. I've been at Cloudera for, how long has it been now actually? I'm a data scientist, I should know this. I think it's been like 16 months or so, roughly speaking. Yeah, that sounds good, 16 months. Before that I was at Google. I worked at Google for a little less than 4 years. I did kind of like a proper tour of duty at Google. My first job at Google was working on the ad auction. So you do a search on Google and ads show up. That was me. You're welcome. Thank you all who have heard that joke before for laughing politely. I appreciate that. After that, I worked on a bunch of data infrastructure stuff. So I worked on things like logging, building dashboards, building experiment frameworks, doing friend recommendations, all this kind of stuff, all trying to analyze user behavior. A lot of it got used in Google+, a lot of it got used in Google News, a lot of it got used in Google Mobile Search. So I've done pretty much everything with respect to data that you possibly can do in about a 4-year span, roughly speaking. So now I have this really cool job at Cloudera, where I am a data scientist at an enterprise software company that, as you probably suspect, doesn't have a ton of data. So I mostly just get to kind of go around and work on problems that I think are interesting and then go talk about it. So it's a pretty sweet gig. They pay me and everything. It's really cool. Anyway, so let's get started. That was a lot of the about me. There's one more thing about me, and it's this tweet I did. If I was to die tomorrow, this would be like my major contribution to Western civilization. And that is a proper, defensible definition of what is a data scientist. So my definition is someone who is better at statistics than any software engineer and better at software engineering than any statistician. And to the extent that being retweeted a lot on Twitter is a sign of credibility, this is a pretty popular definition. People typically kind of, within sort of the constraints of 140 characters, this is a pretty good definition of what it means to be a data scientist. All right. So a lot of people my grandma asked me what is data science, that kind of thing. Today we're talking about analytical applications. And so I thought it would be useful if we started out by talking a little bit about what we mean by analytical applications, or what exactly I mean when I say that. Since our field right now is kind of overrun by big data and data science and all these words that have a lot more meaning sort of poured into them than any sort of their size can support, if that makes sense. Right? There's a lot of different ideas floating around about what this stuff means. So I want to tell you what I mean by analytical application. And what I primarily mean is sort of applications that allow users to work with and make decisions from data. And I realized as soon as I wrote that down, that was way, way, way too broad of an application, of a definition, right? What application possibly doesn't have data? So this might have to be more of a kind of let me show you what I mean exercise, than a sort of define it precisely sort of exercise. But let's talk a little bit about this, right? So the canonical example, right, has got to be dashboards. And everybody knows dashboards. Dashboards is it's like data science 101, writing a dashboard. I think this is something based off of ClickView. If you guys have ever seen ClickView, it's a tool that helps you build dashboards off of relational databases very quickly and easily. And there's all kinds of dashboarding tools. There's you can use D3, you can use ClickView, you can use MicroStrategy, you can use Tableau. There's all kinds of stuff you can do. And it's sort of funny because one thing that's strange to me about these tools is they all support pie charts. You know what I mean? Or even worse, actually, in some cases, 3D pie charts. And it seems like there should be some kind of warning or a pop-up box or you guys remember Clippy, right? Clippy for Microsoft. If it was imagine Clippy, except it was a little headshot of Edward Tufte, and it was you're about to use a pie chart, are you sure? You know what I mean? Or try to talk you out of it, or recommend a better data visualization method, right? There's I'm not sure about this, I'm doing some work on it, but I think even in the case of if you're trying to illustrate how much of a pie has been eaten, there's a better choice of graphic than a pie chart. Nonetheless, right, dashboards are a great analytical application. There's a lot of more fun stuff we can talk about. Have you guys seen Crossfilter? Does anyone see Crossfilter out of the D3 guys, Mike Bostock and those guys? Crossfilter is fascinating. So if you go you Google Crossfilter, this will come up. This example application I have of using Crossfilter is showing flight information, flight arrival times, flight delays, all that kind of stuff. And it's this really beautiful, fantastic, interactive application for analyzing large amounts of time series oriented data, interactively, right? So there's all this data. you get this fantastic user interface for like working with it, interacting with it, even though you yourself don't really know D3.js, you don't really know, where this data came from, or maybe even what an airplane is. Doesn't matter, you can still use this application to do really kind of very interesting analytics. Some topical examples of analytical applications. You guys, everyone enjoyed the election the other day? It was pretty cool, right? Yay. Wow. Yay. All right. This is San Francisco, for God's sake, right? We voted like 97% for Obama. We should be happy. Anyway.
84.
84 was that what it was? 84? Okay. It's probably like lower than 2008, isn't it? That's kind of surprising. The New York Times, again, this is basically, I basically just put a picture of Mike Bostock in the stock, like this is God. Did this wonderful, wonderful, wonderful set of visualizations. I know it was like for you guys. I'm at work on Tuesday, and I'm sitting there, and it's like 5 p.m. and election results are coming in from all over the country, and I'm on the New York Times website using their like visualizations. And I know I should go home and watch like TV with my friends and watch the election results come in, but I don't want to, because these visualizations are so good, and this is like such a better way to consume information about what's happening in the election right now. So this particular graphic I love. This was the vote differential by county relative to 2008. So the red arrow is sort of moving to the right there, which I suppose is appropriate, are counties that shifted to vote more for Romney than they did in 2008. And then the blue arrows, which are a bit more sparse and kind of tougher to see, are votes shifting towards Obama in different counties. So you have this big, really nice graphic of like all these different shifts, and you saw this in real time. As the data was coming in, as like county results were being reported, this graphic was being updated. And actually, I'm pretty sure it's still up, so if you want to if you have a laptop open or a phone or whatever, probably mostly a laptop, you want to go play with this, I highly encourage it, and it will not bother me at all. You won't hurt my feelings or whatever. You could zoom in on individual states and then mouse over counties and like just literally see, in particular in Florida, you could see the ways in which Tampa was voting substantially similar to how they did in 2008. And if you knew anything about electoral politics, you would know that's a really good sign for Obama. That was a very positive thing for him. It was more likely than not, he was going to win because Tampa was voting the way Tampa did in 2008. Like that kind of thing. All right. So when I'm talking about analytical applications, I want to make a distinction here, and it'll be an important distinction in the rest of the talk, between an analytical application and a framework or a tool that helps you build analytical applications. So in these examples, this is all tool plus data, right? The sort of complete set, formatted and packaged in a way that makes it available to a less technical user. Someone who does not necessarily know nearly as much about data analysis, visualization, all that kind of stuff as you do. That is, in my mind, an analytical application. Things like R, SAS, QlikView, all these different tools, these things are things you can use to build analytical applications. They are not analytical applications in and of themselves, as I am defining them for the purpose of this talk. Does that make sense to everybody? Right? It's like I could build something very cool with R, I could build a cool website. Actually, did you guys see the RStudio guys today released a new framework called Shiny for doing like R web apps? It looks really sweet. I'm like totally excited to play with it. But anyway, that's just an important distinction. I want to throw that out there. So I want to talk first a little bit about how we develop analytical applications. And this is in a general case. This is not in a Hadoop case quite yet. We'll get there, but we're not quite there yet. And so again, being topical, I want to talk a little bit about the sort of process of predicting who was going to win the presidential election, right? Because if you guys don't know who this is Nate Silver, and he is the patron saint of math at this point for all intents. He's a blogger, statistician who worked as a contractor for the New York Times, in a very popular website or weblog website called 538.com. The New York Times picked it up. He does electoral predictions. He used to do baseball predictions, now he does electoral predictions. He is a rock star. He's like really, he's the guy right now. So a lot of different people were working on models for predicting who was going to win the presidential election. Though Nate was maybe the most famous one, but there were a few of them, and I want to talk about them right now and talk about sort of the key differences between them. So first one, this is actually the oldest one I think that's around right now, which is the Real Clear Politics model. Okay. If you go, this is realclearpolitics.com. They have kind of a right-wing sort of slant, as like in terms of their commentary and stuff like that. But they are like honest, and they post all these polls, and they give like great data, and they make it available to people. And the way they predict which state is going to win is they take all the polls for a given state, and they just compute the average of them. And the guy who's going to win the average is the guy who's going to win the state, roughly speaking. And there's like different sort of strength levels here with respect to how likely they are to win the state, right? Is it like far, far away from like the 0 point, or is it pretty close, like that kind of stuff. So this is a really simple model, right? This is just, here's some data, average it. Not rocket science, not very advanced statistics, right? It's very, very transparent. It's totally obvious what they're doing. You can see the raw data on their site. You can check their calculations. You can verify they're true. And as far as the data application goes, it provides actually like sort of many nice interactions. So I can like take one of these maps and I can change states, and I can say, oh, well, I'm going to assume that Colorado is going to go to Obama. Like, what are the implications of that, right? So fairly like basic interactions, a little bit of like interactions you can do with this, both in terms of changing the inputs, like assuming a state is going to go differently, what are the implications of that? And then in terms of the outputs and like doing like drill downs and visualizations and stuff like that of the data. So really kind of like good, simple, straightforward analytical application. Now, 538.com, much more complicated model. If you guys, so Nate Silver timed things very well, wrote a book called The Signal and the Noise that I'm reading right now. Have you guys heard the allegory of like the fox and the hedgehog? The hedgehog knows one thing really well, the fox knows lots and lots of different things. And it's a way of describing different ways people see the world. Some people, it's like they have like their thing and like that's it. And they just, this is the model, this is the preconceived notion. Foxes are much more like, let me try lots of different things and see what works. And see like which ones are consistent with each other. They're sort of I don't want to like put value judgments on these things. God, I've been living in San Francisco too long. The Fox model is better. Yay. There we go. So Nate uses lots of different things as inputs to his model. He uses the state polls. He uses economic data. He analyzes correlations between states. So if I know something about how the polls are in Wisconsin, that tells me something about how people are likely to vote in Minnesota, because they're very demographically similar. All right? Lots and lots of different things. Much more complicated than just, say, a simple averaging of the polls. Not transparent, though. Fairly opaque. Nate doesn't share his model. It's a proprietary thing. It's kind of like locked down. It's his paycheck, basically. He's not inclined to like open source it to people. He also provides some simple interactions in the same way Real Clear Politics does. I mean, so you can basically mouse over the states and see the probabilities of the wins. And then down here, although it's a little tough to see, there's a histogram of like different electoral probabilities and how likely different electoral outcomes are. So same kind of basic simple interactions, but with a much richer UI. All right. So last but not least, the Princeton Election Consortium, and this is kind of like, this has become like the cool kids. This was the place you go if you were like a really statistician kind of badass, and you wanted to like keep track of what was going on in the election. Again, it's a fairly simple, fairly open method. They take a recent sample of state polls, they grab the median. Pretty simple to do, right? And then they have this fairly complicated polynomial for taking that median, converting it into a probability, and then generating a big electoral outcome based on those probabilities. So it's a very kind of like, it's basically a kind of cool math trick that makes something very complicated very simple to actually compute. So for instance, the 538 model runs like something like 25,000 simulations. That takes a few hours to do, apparently. This thing can be recomputed in like 2 seconds, that kind of thing, right? So very transparent. Relatively simple model. Again, like it's just state polls, medians, and this polynomial model. That's it, right? But the thing I really loved about this was that it has a really nice, rich set of interactions. And rich in the sense that it actually lets you change the assumptions about the input data. You can assume that the population as a whole, like say you can assume that the polls are biased 2% in favor of Romney, or 2% in favor of Obama, and then recompute things in a Java applet they have on the site. It lets you see how those kinds of bias assumptions affect the downstream model. And you can see like shift all the probabilities in the states. So you can see like, the polls aren't perfect, right? Although they obviously did a fantastic job this time. So if they're wrong by X%, what are the implications of that? What would happen in that situation? So you get like a really much richer, it's a much richer way for you as a user to interact with the inputs to the model and not just their outputs. It's not just like a pretty way to consume it. You can actually change the assumptions the modeler made going in the first place. And that was pretty cool. I like that. All right. So how do these guys do? How did everyone do? This is another useful website. IsNateSilverAwitch.com. It's actually it's kind of the answer apparently right now is probably. I love this website. The great thing was like, there's an API for the website as well. So if you like do isnatesilverwhich.com/update.json, you get back a little JSON object that has like a probability. Like, it was like 61%, I think, the other day, something like that. So listen, Nate did really well. Actually, to be honest with you, all three of these sites did really, really well. I'm gonna pop back to PEC just for a second here. All three models, or sorry, I should say, both PEC and Real Clear Politics correctly predicted 49 out of 50 states. People missed Florida. They did not get Florida. The average of the polls made it look like Florida was more likely to go to Romney. It's not definite yet, but at this point it looks like probably it's going to go for Obama. Nate managed to get all 50 states. He got everything. His Florida probability was something like 50.3% or something like that. It was like basically a toss-up, but it was stronger for Obama, so he gave it to Obama. Even more so than that, though, these guys did a really good job of predicting not just who was going to win, but the actual sort of percentage of votes in the different states, like what fraction of the vote in Ohio was going to go for Obama versus Romney. CNET did an analysis of this across a bunch of different pollsters, a bunch of different aggregation models, and Nate Silver did the best by far. He beat everybody. He even beat PEC, and beat Real Clear Politics. So, bully for Nate. Cool sort of like fun thing that came out of this. People started Nate Silver Facts as a hashtag. Let's go through a few of them right now, just because they're fun. Results ask Nate Silver if they're significant. I kind of want something here like Nate Silver's anecdotal experiences are statistically significant, or something like that. You know what I mean? Nate Silver does not breathe air; he just periodically samples the atmosphere. Was a funnier one? Okay, that's good. Next one's mine. Let's see how this one goes over. Nate Silver knows the mean of the Cauchy distribution. Nothing. Not really. The Cauchy distribution is a probability distribution where the mean is undefined. That's why it's funny. Anyway, it's good to know where I stand there. Anyway, I'm working on that. So here's the rub, though. Somebody beat Nate. Nate Silver Facts, right? Somebody actually beat him. An expert. People know Marcos Moulitsas, the Daily Kos guy. You've heard of this guy, right? He actually did better than Nate in predicting the swing states. And he posted it on his blog. He did it. He proved it like the day before he posted, "These are my predictions," and then the day after he compared it to what actually happened. And he did better. He basically took all the polling data for the individual swing states. The photo was designed to be like kind of sad Nate Silver. I mean, he might not be sad. He might just be like working really hard. It's tough to tell. But Kos did better for a couple of reasons. One, he knew that Colorado and Nevada, the polls tend to underestimate the Latino vote. And so he basically bumped Obama's margin, his prediction of how much Obama would win by, in those states higher than the polls. And that turned out to be the case. And the other thing he did was he knew that apparently in Iowa, the Des Moines Register, whatever poll they do has correctly predicted like within, much tighter than anybody else for like the last 20 years. So he didn't use the average in Iowa, he just used that one poll. Those are basically like the two tricks he did to outperform Nate Silver's very complicated, very advanced statistical model, right? So you can think of this as like basically he is an expert. He knows a lot about politics. He like lives and breathes this stuff. So he's capable of basically doing a better job perhaps of filtering data than Nate's model can, right? He can bring some expert judgment to things, some priors. The model probably wouldn't feel comfortable making. He can do that. So I guess what I'm saying is Marcos, again, also predicted every state correctly, including Florida, right? So very advanced, like sort of fox versus hedgehog kind of models are amazing. And it's like clearly Nate Silver is some kind of witch. But nonetheless, having an expert armed with really very simple data, just like literally here's the polls, right? No fancy models, nothing like that, but an expert opinion can do just as well, if not better, than like a fairly like fancy advanced technique. I don't know if this is like the right audience to be sending this message to. Maybe like the business people would feel better hearing this than necessarily people in this room. Anyway, those things. So the analogy I draw here, the analogy I draw between Real Clear Politics with their very simple model, Nate with his very complicated model, and then like Kos with his fairly advanced knowledge, his expert knowledge of politics, with a respect for data. I guess it's sort of the big caveat there, right? Like expert knowledge plus data, not expert knowledge by itself. Index funds, hedge funds, Warren Buffett. So if you don't know anything at all about politics, and you're basically making a bet on the election, just doing a simple average of the polls is probably a really good idea. It doesn't require that much work. You don't really need to know that much statistics. It's 98% effective. Like this is really good, right? If you need a little extra on top of that, if getting the exact sort of like best prediction of popular vote is really important to you, then you need something more like a Nate Silver model. You need something like a hedge fund, right, where you're really looking for absolutely every single edge you can possibly get. Optionally, maybe even better than that, be Warren Buffett, right? Be an actual expert who has a certain like perspective and a way of interpreting data that outperforms even like the fanciest hedge fund models, at least over the long term, right? All sort of valid approaches here depending on what your level of expertise and what your skill sets are. All very, very effective, okay? So, if I may, right now, that was my kind of general analytical applications. This is what I think of analytical applications. I sort of assumed when I came here, this is a San Francisco audience, I assumed Hadoop expertise. I assume many of you know more about Hadoop than I do, to be honest with you. I don't know if that's fair or not, though, based on some conversations I had so far. So how many of you are familiar with Hadoop? Let's do the less embarrassing question. Okay. Most people are like reasonably familiar with Hadoop. But I see like not every hand went up. So I'm going to go through, this is kind of Josh's standard, this is Hadoop spiel. And hopefully if you know what Hadoop is, I provide a little bit of color commentary that makes it perhaps more interesting than the 97 other this is Hadoop spiels you've heard before. But I'm asking you to sort of bear with people who haven't done this, because if we don't do this, the rest of the talk's not really going to make any sense to them. Okay? So, the way I normally do Hadoop, you know what, I think I just realized, I'm pretty sure my iPod is on, and I'm like hearing the music right now. That's what it was. I'm not crazy after all. That's really, thank God we're recording this talk. So, brief introduction to Hadoop. Best way to understand a new technology is always in terms of technologies you already understand. All right, so let's go back in time 11 years, 2001, back when I graduated from college. Sort of dating myself there. Usually when I say that, like half the audience will laugh and be like, oh my God, he's so young, and the other half will be like, oh my God, he's so old. Anyway, data source in 2001. If I have a whole bunch of data and it's 2001, what are my options? What is available to me? What technology can I use? Option number one, and it's a very good option, is a database, right? Relational databases. So relational databases have structured schemas. I specify ahead of time, this is how my data will be structured. Database, I promise that all the data I give you will match the structure for this particular table, okay? Super cool thing about databases. You can do really very intensive processing on data where it is stored. You send a little tiny itty bitty SQL query to a database, and it does like a massive amount of processing as a result of that query, and it gives you back a relatively small answer. And that's kind of a cool idea, right? That's much better than having to say, suck all the data off the database, do your very simple processing on it, and then like maybe write it back again. So this is a great thing about databases. In 2001, databases are like pretty reliable, but I have probably like a backup somewhere just in case. And they tend to be a little bit expensive at scale. It's really, instead of a lot expensive at scale. All right, that's option one. Option two, a filer, a network attached storage, a storage area network, something like that. Cool thing about filers, there's no schemas whatsoever. They're just files. I can store anything I want. I can store images, I can store video, I can store audio. Doesn't matter, I don't need to cram it into some database schema ahead of time. This is very cool. Downside though, there's no data processing capability. So if I have to do any processing on this data, I'm back in the situation where I have to kind of like pull it off, do whatever processing I'm going to do, write it back again. Not very performant. Networking is a big bottleneck. This is a problem, right? These systems are super reliable. In fact, that's what you're paying so much money for. They basically are promising you in no uncertain terms, I will not lose your data. And again, we have the problem where they are a little bit expensive. Again, a lot bit expensive at scale. All right, so that's 11 years ago. Then this happens, right? We have this sort of ridiculous explosion in data. In fact, it exploded so much that the image went off the slide, apparently. So it's just completely out of control, right? Ridiculous growth in data. Web application stuff, mobile stuff, sensor stuff, like data. We have data coming out of our ears, right? It's absolutely ridiculous right now, okay? We also have what I think of as a shift in data economics. And this is important, I think, to data science in particular. So this is classical data economics. Classical data economics is all about return on byte. How much does it cost me to store this amount of data? How much value can I extract from that amount of data? If the value is greater than the cost, I keep it around, right? I keep it online. If the value is less than the cost, then I put it on tape, or I just throw it away. Basically the same difference, right? That kind of thing. That's sort of classical data economics. Last 10 years, though, we have what I call big data economics. This is me obviously abusing a marketing term for my own nefarious ends. Hope you guys will forgive me for it. Big data economics is the case where no individual record is all that valuable, but having an enormous collection of records is incredibly valuable. Everyone in this room right now has a web page on their phone or on their laptop or whatever, right? You have a little cache of 100 web pages. Not worth anything. Everybody has web pages, not a big deal. But if I have 8 billion web pages, I can build a search engine, and that's very valuable. Everybody in the room right now has a receipt probably in their pocket, or a couple of receipts. Not really worth much of anything. If I have 10 billion receipts, I can build the world's best product recommendation engine. You can build data products by analyzing the relationships between a very, very, very large number of things that have no value, right? That's kind of the cool idea. So value going up there, kind of like Metcalfe's law for data in some sense. Data that has strong relationships, where I can analyze those relationships cost effectively, can be very, very valuable, all right? So we have a lot more data. The technologies available to us in 2001 to store it are really expensive. What do we do? This is really what Hadoop is designed to solve, essentially speaking. This is what Hadoop is about. The way to think of Hadoop, if you know databases and you know filers, is to combine aspects of both of these systems. So Hadoop, first and foremost, at its core, is just a file system. You can store anything you want on Hadoop, just like you would using a filer or a SAN or something like that. Like a database, though, we're going to send the code to the data. We're not going to pull data off, do processing on it, and then write it back. We're going to send a very tiny amount of code to a very large amount of data stored in the Hadoop cluster. We're going to process all the data there. All right? So process data where it's stored like a database, store anything you want like a filer. Of course, there's no free lunch, right? We'll talk about that a little bit later, but that's really basically the way to think about it. So core components of the system. Hadoop's distributed file system, right? This is based on Google's file system. Google wrote a paper about this, they published it, and the Hadoop guys use it as the basis for that. Most people know file systems, right? Like file systems are made up of blocks. Well, like each file is a whole bunch of blocks, and the file system keeps track of which names map to which blocks. On your sort of laptop file system, the blocks can be like 4 kilobytes, like pretty tiny. Hadoop's all about big, big files, so typically more like 128 megabytes for a block, 256 megabytes for a block, very big blocks. Each block is replicated to multiple nodes in the cluster 3 times. This is basically done to ensure reliability. I've had people ask me, Josh, how did Google ever come up with this in the first place? And the reason was, and people don't think of this now because Google's like such a unbelievable behemoth. But back in 2000, when they were developing this stuff, Google had no money. And there was no AdWords, there was nothing like that, right? There were still massages and good food, but there was not really money to pay for it. So they had to buy very cheap, crappy hardware. And it was hardware that failed essentially like all the time. And after being burned a few times by having like the hardware that contained their data failing, they decided to start copying, like manually copying data to multiple systems, multiple like nodes in their cluster, or multiple computers, right? So that if anyone failed, that was okay. They had it stored someplace else. When they developed GFS, it was really just about how do we make this thing we're doing already manually automatic and more efficient, so we don't really have to do it anymore. That was really the idea, right? I'm all about innovation drives constraints drive innovation. It'd be weird if innovation drove constraints. Constraints driving innovation, that makes more sense. Constraints drive innovation. The reason like Google had to do this was because they didn't have any money. They couldn't go buy a really expensive filer. They couldn't go buy a really expensive database to keep this stuff around. It just wasn't an option for them. All right. So that's HDFS. The processing framework, MapReduce. So MapReduce has 3 stages to it. There's the map stage, which is embarrassingly parallel. We're going to take each kind of input record from our file, and we're going to process them independently of every other record in the file. And we're going to emit key value pairs. Okay? The shuffle stage is kind of the brains of the system that's actually implemented by the framework itself. You don't have to do that yourself. What we're going to do is take all those key value pairs the map stage spit out, and we're going to sort them so that all the values for the same key are grouped together. So big block for key 1, big block for key 2, so on and so forth. Then in the reduce stage, we're going to process all the values for the same key in one big step. Just iterate through them and do whatever processing we need to do on those values. All right. Key idea here again, kind of like a database, we're processing data where it is stored. Map, we write a little map function in Java or Python or whatever. And we write a little reduce function, same kind of thing. We send it over to the cluster, and the cluster has a way of executing our code against the data itself, and then aggregating the results for us, doing all the shuffle. MapReduce, it seems kind of simple. It turns out there's an enormous variety of problems that can be mapped into one or more MapReduce jobs. You'd be amazed, and there's lots of books online if you're interested in understanding how that works. The genius of MapReduce for me as a software developer, when I first started using it, was the realization that if you write your MapReduce in a sane way, and you're like not sort of like intentional evil about it, once you've written it, you're done. If the data volume goes up by 2, you just throw more hardware at the problem. You don't have to rewrite the system. I know it was like for you guys, before I had MapReduce, I spent a lot of time rewriting code I had written when the data volume went up by 2 or by 5 or by 10. That was the way I spent a lot of my time. And I don't do that anymore. And it's awesome because my time is very expensive and I have lots of stuff to do and blah, 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 right? So it's like this is like one of the sort of key, really maybe obvious but kind of genius parts of Hadoop to me. And I'm going to talk about the other one a little bit later, all right? But that's good stuff. Okay. All right, on to the fun stuff. Developing analytical applications with Hadoop. Again, keep in mind here when I'm saying analytical applications, I mean code plus data. I'm not really talking about frameworks so much. At least I'm going to try not to. I'm probably going to fail, but I'm going to give it a shot. Okay, that kind of thing. Code plus data, analytical applications. All right, rule number 1 in developing analytical applications on Hadoop. It's really just kind of a general rule. Novelty is the enemy of adoption. If you take something and you give it to people and it's like completely new and completely different, it will freak them out and they won't use it. So the first analytical applications I developed on Hadoop, after I left Google, started working on Hadoop stuff, were really about looking for things people were doing now on large amounts of data, but were doing badly or slowly or whatever. And that really were sort of very easy and nice to translate into Hadoop. So they could basically be doing essentially the exact same thing, ideally like literally running the same commands, the same application they were running now, except running it on Hadoop instead. All right. So the first application like this is I wrote a project called Seismic Hadoop. So for various reasons that are not worth getting into right now, I got very interested in seismic data processing when I started working at Cloudera. Seismic data processing, this is basically how we find oil, essentially. We send boats that have sonic waves, like air guns kind of attached to them, and sonic receivers, and we bounce sonic waves off the different sort of sub-layers of the Earth, and we record the reflected waves as they come back to the surface. We analyze the data, and we can basically sort of see, it's basically like doing an X-ray for the Earth. You can kind of if you do it properly, you can actually see the substructure of the Earth, and it'll let you figure out where things like oil and natural gas are. And I love this field for a couple of different reasons. The guys who use it are called geophysicists, and they've been doing open source software on large data sets since the 80s. And so I sort of discovered them. There's a little tiny community of these guys that work at Chevron and Exxon and all these companies that no one's ever heard of. And they have these great open source tools they've had around for 30 years. So I took one of those tools, actually called Seismic Unix, and I adapted it to run on Hadoop. So we can actually take, essentially all you're doing in seismic processing is filtering things, sorting things, and adding things. That's fundamentally, that's the heart of seismic data processing. Hadoop, good at lots of things. In particular, it's good at filtering things, sorting things, and adding things. These are all Hadoop strong suits. So I literally could take their exact same commands they'd be running on a file stored on their desktop, and take that command and execute it on data that was stored in a Hadoop cluster. They didn't have to change anything. Now, I, behind the scenes, had to do some kind of magic to parse the command and figure out which stages had to be turned into MapReduces and which stages had to be, or which stage was the shuffle and what was the reduce and all that kind of stuff. But their experience was absolutely no different, right? No change whatsoever. This is very good. This is very key. This is the novelty is the enemy of adoption. And the Hadoop community realizes this. And so, in my opinion, really the best way to get started on Hadoop is Apache Hive. So Apache Hive is a data warehousing metaphor on top of HDFS and MapReduce. You have a SQL-based query language. You create table, insert things, select things, group by, where all that stuff sticks around. Okay, like sort of the basic. You can look at the code and like roughly figure out what it's doing if you know relational databases really well. Hive, of course, has some like MapReduce specific extensions. There's some things that like make sense in MapReduce that don't make sense in SQL and vice versa. So there's like certain kind of MapReduce operations. There's some like analytic functions like lag lead operations don't really make sense in Hive, and so that you can't do that in Hive, like that kind of thing. But it's a great way to get started with Hadoop. Again, novelty being the enemy of adoption, right? So all the tools, like all the different Tableau, MicroStrategy, Cognos, business objects. Actually, I don't know about either one of those, but they connect to Hive and they understand Hive. They speak Hive. Hive like acts like tables. One of the things, though, we do this a lot. We borrow these abstractions. We have developed. We in the sort of analytical data analytics processing community have developed an enormous number of really very effective abstractions for working with data. Spreadsheets, right? Spreadsheets are an abstraction. We can use them for everything, and we do. It's one of those things where like spreadsheets had an original meaning, right? Like a spreadsheet was a like actual paper thing that was used in accounting, like 40 years ago or whatever, right? But it's become, because it was so useful and so general purpose, it's actually become an abstraction that we apply across all kinds of different data sets, right? So we borrow these kinds of abstractions. Hive does this, Datameer does this, Karmasphere does this, all these different tools built on top of Hadoop to provide you with star schemas and relational data, relational database things, kind of semantics, right? All of the objective of making it really easy to get started with Hadoop for you, all right? Now, there's a couple of problems with this. If you just see Hadoop through the lens of these abstractions that you're familiar with, if you just see Hadoop as like a really big spreadsheet or as a like really big honking relational database, you don't really fully get the power of Hadoop. You don't really fully get what you can do with it. And I want to talk a little bit about that in the rest of this talk. I guess my feeling is, if you come to Hadoop and you're expecting spreadsheets and you're expecting like very high performance data warehousing stuff, you're probably going to be disappointed. It's not going to be nearly as good at like the 40 years we spent working on spreadsheets or the N years we spent working on relational databases. There's a guy called Mike Stonebreaker. Anyone ever heard of Mike Stonebreaker? Right, he's a database guru, Postgres, like he's a longtime database expert, knows all this stuff. And he loves railing on Hadoop, loves ragging on Hadoop. Kind of like troll's not the right word, but troll might be the right word. And the only thing I can figure is that his objection when it boils down, like as I see it, is Hadoop is not a relational database. And I don't know who the hell told him it was. And I'm not sure, I would like to find that person and have like a stern talking to with them. Because if you're using Hadoop like a relational database, you're not really using it the right way, all right? That's kind of my, yeah, all right, that's good. There's some things we can do to address this. There's some things we can do to make the Hadoop experience be more like what you're used to with a relational database. And a couple weeks ago, this is where the advertising section of the talk kind of kicks into high gear. We at Cloudera released a project called Impala. This is Cloudera Impala. This is our fast query engine on top of Hadoop. This is 100% open source, Apache licensed. The GitHub link's up there. You can go download it and play with it, and I highly encourage you to do so. And this is where we take ideas from big relational databases, from massively parallel processing in relational databases, and we adapt it to data stored in Hadoop, so that you get much faster, borderline interactive, depending on the query, queryability with Hadoop. You basically make Hadoop feel much more like the relational database abstractions that you're used to working with, right? And this is a good thing. This is how we sort of try to solve some of the like leaky abstractions, not really the right term, but like abstractions that like aren't really quite what abstractions don't necessarily like fulfill all the contracts of the abstraction, I think. They aren't really quite exactly what they claim to be. They're sort of like that, but they're also different in some other ways, all right? But more than that, and what I really want to talk about tonight, and it only took me about 40 minutes to get to it, is how we move beyond these abstractions. right? How do we actually kind of let go of the ways that we think about data, the spreadsheet orientation, the relational database orientation, all that kind of stuff, the ways that we kind of currently think about building analytical applications and working with data. And I have a few tricks that I want to suggest and throw out there, right? And I think the first one I want to say is we want to, first and foremost, make the abstractions concrete. And this is important. We're not trying to build a relational database, a star schema. A star schema is a really useful abstraction. It is a pattern one can use across all kinds of different data analysis problems. So I can come up to a relational database, see that it has a star schema, and if I know nothing about the problem domain, I'll at least be able to understand roughly how to query it. Right? I'll understand there's a fact table and there's some dimension tables and snowflakes, and I can basically get it, right? But if we just try to take that model and map that perfectly onto Hadoop, first of all, it's not going to be possible. Hadoop isn't a relational database. It's not going to be reasonable to ever do that perfectly, right? But my bigger concern is we're going to miss the sort of the possibility to look at new ways of creating analytical applications that are appropriate for different domains. And so what I really want to move to when we're talking about building analytical applications is actual concrete applications. How do I make this patient data available to this doctor who doesn't even understand SQL? This is the world I want us to move to. Here's I don't mean to pick on medical people, but here's a biologist, right, who has to work through 17 terabytes of genetic sequencing data, and doesn't even understand the shell, right? Doesn't know any of this stuff. Maybe knows a little bit of Perl at most, right? This is a really new, fun challenge for us. We have a new set of users who have to work with larger data sets than they've ever had to work with before, and they have far fewer technical skills. So our job as data scientists is to fill that gap, is to fill that application gap. And my feeling is that in the process of doing that, we will discover new abstractions and new patterns equivalent to spreadsheets and equivalent to the spreadsheets, relational databases, star schemas, all the stuff that has been so powerful and served us so well for the last 30 years. I think we're going to be able to discover new ways of doing this stuff much better on top of Hadoop. And I have some feelings about how this is going to go. Before I do that, quick shameless plug. Teaching a data science course next week. Cloudera, about a week ago or so, I read a blog post announcing our new data science course. It's going to be 3 days. Basically, it's essentially the course is about building a data product. It's about building a recommender system in particular. Really, the course is about how to munge data on Hadoop. Here's a bunch of web logs, here's a bunch of JSON data, here's a bunch of database data. How do I combine it all together and prepare it to be input to a machine learning model? That's really kind of what the core of the course is about. I want people to see Hive and see Hadoop and see the way to work with it the way I work with it and the way that I see it after having done it for 5 years and done it for Google and all that kind of stuff. So I think it will be helpful, at least setting a very kind of baseline minimal level of understanding of what you can do differently when you're analyzing data on Hadoop. All right? So shameless plug over. Analytical applications I love. Things, Hadoop-based things that I really very much deeply enjoy. This was actually kind of great. So Google had this, basically everybody has this, Twitter has it, Facebook has it, an experiments dashboard. So I, average developer, right, just regular software developer, can come up with some experiment, some A/B test, some multivariate test I would like to try. I have a system for deploying that experiment into production, automatically gathering data on it, automatically writing that data into a Hadoop cluster, automatically running MapReduce jobs to compute metrics over that data, compute confidence intervals over it, and then populate a database that then shows me the output of that. That is a full-scale analytical application, right? Soup to nuts. The UI for me is I change a configuration file and I push it out to production. And then I wait 24 hours because obviously this stuff's very batch. And I come back and I have a dashboard that I can now interact with and get information about how my experiment is performing. This is one of those problems that I think has basically been solved over and over and over again, and that may be a theme of tonight actually, dashboards are a problem that have been solved over and over and over again. I think this one's in the same boat. Everyone does this themselves. There's not really any reason to, insofar as I can tell. The math is basically the same. I don't really think there's any sort of secret sauce to developing these systems. Some company, ideally founded by one of you, Should start a company that basically sells this as a product. Here's the Java, PHP, okay, maybe not PHP, Python, C++ libraries that write logs. Here's the language you use for calculating metrics on those logs. Here's the dashboard that computes confidence intervals off of that data. That's an analytic application, soup to nuts, right? Powered like basically purely, not purely by Hadoop, but with Hadoop at its center to do data processing, right? Great, great stuff. Making people who don't know statistics, who don't know the right way to compute like confidence intervals, whatever, make this sort of available to them. Give them a sophisticated interface for understanding how their ideas are performing. They just have to have the ideas. You have the statistics expertise. It's all embedded in the application. All right. Adverse drug events. This is I think the second project I worked on at Cloudera. Adverse drug events. People, you're taking a whole bunch of drugs and something bad happens to you. Something unanticipated happens to you. There's potentially some kind of interaction between all these drugs you were taking, and it causes, you get sick, you go to the hospital, you die, whatever, anything like that. It's nice to kind of trivialize death in that way. Sorry about that. A few million of these happen every year. When they do, they get reported to the FDA. The FDA maintains a database, and they actually are kind enough, data scientists such as myself, to publish an anonymized sample of this data and make it available online, right? Who's whistling? Yeah. That wasn't like you're running over a whistle, right? That was just okay, anyway. They make a sample of this data available online. Now what we're looking for is drug interactions, okay? So the person's taking a whole bunch of drugs, there's a whole bunch of reactions associated with it, right? So we want to analyze basically sort of a kind of a combinatorial explosion of all the possible drug interactions we have in this data set, all right? This is one of those things where you start out with like 400 megabytes of data when you start the analysis, like just a very tiny, small amount of data. And in the course of doing it, you generate about two terabytes of data, right? It's like 4,000 times roughly more data than you had when you started, right? Because you're basically a big, huge combinatorial explosion of all the different drug interactions. This is also an analytical application to me, and let me tell you why. When I'm doing this analysis, in the same way when Nate Silver is building his model, I am making an enormous amount of assumptions about which patients are similar to each other in some sense. I am assuming that a 52-year-old and 53-year-old are similar. I am assuming that males and females are similar. I'm basically creating a bucketing scheme to say, okay, everyone in each of these buckets by gender, location, age, whatever, is essentially the same for analytical purposes. So these decisions, these assumptions I make at the start of the modeling process have profound implications on what the eventual output is going to be. And I am not, in any sense, like an expert in this stuff. I'm not an epidemiologist. I'm not a biologist. I'm nothing like that, right? So the assumptions I make when I conduct the analysis certainly would not be necessarily as good as the assumptions an expert would make, right? But running this pipeline is about 20 MapReduce jobs. It's actually a series of pig scripts, pig being another high-level MapReduce language, that executes this entire thing. And so the thing to do to make this an analytical application would be to configure it so that a biologist can just kind of like click, right? Create a UI where they can just construct a bucketing scheme and then press a button and have it go run over the data, right? And that would be a this is kind of a cool, neat example, and the visualization here is visualizing the output of like the strengths of the adverse event sort of relationships between different drugs. But taking this whole pipeline and making it available to biologists and epidemiologists and people who actually know this stuff would be like really a far better use of my time. Arguably, as much as anything other than like giving this talk right now, actually. So I maybe should, after this talk, I'll go do that. So that kind of thing. I meant for that to be funnier than it came out. Sorry about that. Anyway. Favorite one. I spent a lot of time talking to biologists and doctors, so this is why I want it. The gene sequencing example. If you guys were at HBaseCon, HBase is a sort of a key value store built on top of Hadoop. And the guys at NextBio did a fantastic presentation about how to make the results of a gene alignment analysis available to the biologists who actually understand the biology. They essentially created a search engine for these things. When you do a sort of sequence alignment, if you guys know roughly how gene sequencing works, usually you start with like some kind of reference genome, right? There's like a reference set of pairs. And when you take all the little tiny like sort of SNPs, basically, SNPs overload a term. You take all the little sort of short reads out of the machines. The machine like spins around and spits out like little tiny short reads, like 12 characters, 100 characters, something like that. You go hunt through the reference set of characters, and you find like matching substrings. And it's kind of like, sort of like doing a jigsaw puzzle in some sense, right? What inevitably happens is when you're doing this matching process, you end up with differences. Like there's differences between the reference genome and the genome you just sequenced. And some of those differences are caused by actual biology. And those are the ones we really care about, right? There actually was a genetic difference between this person, and that's why this person has this disease, like that kind of thing. But a lot of the differences are caused by transcription errors. The machines aren't perfect, so they make mistakes, that kind of thing, right? So if I have like about 4 billion or so like little DNA letters in a given genome, there'll be somewhere between 3 or 4 million differences between like the reference genome and the genome I just sequenced. So you take 3 or 4 million instances per genome or per gene sequencing. You sequence a few thousand genomes, and like pretty soon you're talking about like an actual pretty serious amount of data, right? But the biologists don't really know SQL that well, at least by and large, right? So storing this data in SQL is difficult for a couple of reasons. One, it's not really nicely structured for SQL. It kind of has to end up being sort of fairly advanced SQL, i.e. well beyond biologist SQL, right? So what the NextBio and what other folks are doing now is taking this data and indexing it using Hadoop into Solr, and then basically making a query API for biologists that's just a search engine, right? Type in name of gene, boom. Pull back all the variants for a particular genome sequencing that feature that gene. Done, right? And then they have like really, I just highly encourage you to watch this talk. They have some really cool visualization tools so you can see kind of like around that gene, what other genes were different, what correlated genes that you know about historically are different. They just did a really great job with it. And they created this really nice, new, powerful metaphor for doing analytics on this variant data, on this gene variant data, because they were constrained by the fact that the people who knew the biology well enough, the expert knowledge to be able to understand the data, didn't have the technical skills to really be able to do it. And it was like never, ever, ever going to scale teaching the biologists all the SQL they need to do, right? They have like other stuff to do. Like, I'm assuming. I don't know. I don't actually know what biologists do, but more likely than not.
What is the talk called?
Sorry?
What is it called?
So if you just Google HBaseCon, like as one word, and NextBio, it will pop right up. We have all the videos from HBaseCon up on Cloudera's website, and you can watch it right there. Yeah, so that's great stuff. Along those lines, at Strata Hadoop World in New York a few weeks ago, my friend Ryan Brush over at Cerner just did this absolutely wonderful presentation on Cerner, if you don't know, is an EMR, electronic medical record company. There's a few different companies like this out there. They have a system where it's the same kind of thing, so they're providing much more patient data, making it available to researchers, using HBase as kind of a central key value store, Storm to do real-time processing, batch MapReduce jobs to kind of like fix errors, and then Solr on the end here to, again, make patient data available to doctors and researchers. So find me all women who are younger than 37 who had leukemia and this particular like drug, right? Just type it as a query, have it come back, and don't just return the row, right? Return everything you know about that patient to me. Return it like as a patient as a document almost, updated in real time. It's really, really great. Actually, I don't think that talk's online yet, unfortunately, but this is fantastic. I thoroughly enjoyed the talk. So a few themes in here. One is that take advantage of the fact that Hadoop is just a file system, that you can structure data however you want. You don't have to squeeze everything into a row. You can build documents, right? You can use time series. You can use gene data. You can build like complex structures that represent everything you know about your customer, everything you know about a supplier, whatever you want. You can structure the data in the way that makes sense for the problem, all right? Interactive inputs, especially for me on that adverse drug event problem, not just interactive outputs. Let people actually interact with the model. Let them change the assumptions that you're making, right? Let them go take that and then rerun everything and see what the output is. Think of the guys from Princeton Election Consortium, right? Allow me to change the underlying assumptions of the distribution of like the popular vote, of the amount of bias in the polls, and let me visualize the outcome of changing those assumptions. And finally, last but not least, simpler interfaces for users who don't have the technical sophistication. Simpler interfaces that give you more sophisticated answers than you've been able to have before. if we move beyond sort of the notion of the table, spreadsheet-dominated world that we're used to, we think about how we make large quantities of data available and accessible to people who don't have our technical skills, I think we'll come up with some really amazing stuff. And the dream for me, really, is Wolfram Alpha. You guys know Wolfram Alpha, right? So Wolfram Alpha is sort of the online search engine version. You can just type in, what would be something appropriately useless? How did the position of the moons of Jupiter correlate with the GDP of Europe in the 18th century, right? Something like that. Wolfram Alpha can do that, right? Imagine if you could do that on like useful data, like data that you actually cared about, right? How like amazing that would be. And I think Wolfram Alpha is working on this. I think they have a product that's kind of designed to like plug into your infrastructure and do Wolfram Alpha style computable functions on business data, which is fantastic, right? Which is amazing. My concern, though, is that it's going to be kind of expensive, and it's probably going to be pretty proprietary. It's probably fairly reasonable, Ed. You would say so? Pretty expensive, right? That kind of thing. Apparently, it is very expensive, and I'm sure like it's very good, and they're worth every penny. But working towards this, working towards like really Wolfram Alpha for business data in an open source fashion on top of Hadoop, HBase, Storm, all that good stuff. This is what I really want. This is what I actually want at the end of the day. This is my dream. All right. Okay, a little bit, because I promised to talk about this in the talk, and I've got like 5 minutes left, and I'll promise I'll answer questions for like 15 to 20 minutes, it's no problem. But I want to talk a little about moving beyond MapReduce. This is kind of a good news, bad news talk. About a year ago at NIPS, Neural Information Processing Systems, I gave a talk about kind of like machine learning on Hadoop. So you like Google Hadoop machine learning, the talk comes up. And I talked a lot about a framework called Yarn at the core of Hadoop. Basically a way of splitting up MapReduce's sort of core job scheduling, resource allocation systems into separate applications so that you could run stuff beyond MapReduce on Hadoop. Sort of, if Hadoop has a limitation right now, it's that really everything has to be a MapReduce job. And there's lots of other kinds of processing we'd like to be able to do on a Hadoop cluster, right? So the problem right now is we have way, way, way too many frameworks for doing resource allocation and job scheduling on Hadoop clusters. And they're all sort of basically backed by different big, powerful-ish companies, right? So there's a framework called Apache Mesos that came out of Berkeley's AMP Lab, and that's deployed at Twitter. Facebook today made a big push to open source a system called Corona, which is their take on the distributed Hadoop, like job scheduler resource allocation thing, right? We have Yarn now. Yarn's like largely developed out of Yahoo for the most part, right? Actually, I contributed a little bit to it. It's kind of cool. There was a blog post about like announcing the Yarn like beta or Yarn alpha or whatever, and they thanked people who had worked on it. And I was the only person who actually worked on it who had never worked at Yahoo, which was kind of cool for me. So anyway, we have too many frameworks right now for solving the same problem. And I don't necessarily know why exactly this happened or like what horrible thing went wrong, but this is like not good. Because people are going to start building other frameworks, like frameworks on top of it's basically frameworks all the way down, insofar as I can tell. Eventually someone may build something useful, but for now it's just a lot of frameworks. So we'll have a Yarn machine learning framework, and we'll have a Mesos machine learning framework. In fact, we already have two. We'll have a Corona machine learning framework. And we're not all going to be working together on the same thing. And this isn't good. This doesn't help anybody, right? Why Hadoop took off in the first place is because Yahoo, Doug Cutting was at Yahoo and had these sort of insight and genius to say, we're going to develop this thing for Yahoo's use cases, but we're going to develop it at the Apache Software Foundation. So it's going to be open source and available to everyone, right? And then Facebook and Twitter, when they got big around like 2007 and they really needed a system like this, it was there and available for them, and they all started collaborating on it together. That's the key to like Hadoop's success, right? Yahoo putting in the ASF in the first place because Doug insisted on it. Guys like Jeff Hammerbacher and the folks at Twitter insisting that like this was the way to go and they were going to work on it and collaborate, even if they were competitors or whatever, right? And we don't have that right now in the frameworks, in the sort of resource scheduling, job allocation stuff in Hadoop right now. And this is like not good. Like this is like sadness for me. So we've had this Cambrian explosion of frameworks. So I'm a little disappointed. It's not the end of the world, you know what I mean? My hope at this point is like Pinterest will pick a framework and that one will win. You know what I mean? Like, you hope that basically like Pinterest will be like the negotiator, and like Pinterest is the cool company right now. So they'll say, you know what, we're going to go with that one, and like everybody just follows Pinterest, and the problem's solved. So if anyone here works at Pinterest, it'd be awesome if you could make a decision like in the next couple of weeks. That'd be fantastic. If you need any help, let me know. All right, this is my concern. All right, but let's leave that aside. There's a lot of stuff you can do in MapReduce beyond Impala. Like, and one of the great ones is Spark. Spark is like very much worth checking out. If you work at kind of a cool kid startup right now, you're probably using Spark. All right. All these frameworks I'm going to talk about right now are in-memory frameworks, and as such, they are typically much, much, much faster than Hadoop. Right? Hadoop is very disk-oriented. That's why it's nice and reliable. In-memory systems that do analytics in memory are going to be much, much, much faster. A lot of the question between in-memory stuff versus Hadoop is how do I want to like allocate my resources, right? Do I want to devote all the memory on my cluster to loading and analyzing this one data set, or do I want to run like 100 jobs on MapReduce, each of which will take up a little sliver of memory? It's basically just a resource trade-off thing, as it is with most stuff, right? Spark's written in Scala, so if you're like a cool programming language kid, and highly encourage becoming one of those people, it really is the language for you. It's got a nice like REPL, you can interact with data, super fast, and like all these systems, it supports reading and writing data to HDFS. So no matter what happens, whether it's Mesos or Yarn or Corona or whatever, everybody supports reading and writing data to HDFS. HDFS is the standard, it's one, it's over, blah, 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 okay? Its frameworks all the way down to GraphLab, right? GraphLab was developed at Carnegie Mellon. It's basically a lower level set of primitives that has like kind of complex notions of synchronizing data across processes, but still fairly high level. It still takes care of a lot of the really tedious aspects of distributed systems for you. Instead of map and reduce steps, you have update and sort steps. Very, very fast, reads data from HDFS, and the reason I recommend it is because they've written a whole bunch of machine learning libraries on top of it, like out of the box, right? You don't have to like go reinvent stochastic gradient descent, or like fitting a collaborative filtering model or a matrix factorization. It's been written for you already, which is, I'm very lazy, I assume most of you are as well. This is a good thing as far as I'm concerned, okay? A little bit on Yarn. So Google has, Google of course has their own framework, right? Like a system called Borg. It's kind of funny that Borg, it's Google, it's Borg. And Borg is the system that maintains kind of all of Google's compute clusters and manages resource allocation across them. There's a language for sort of configuring Borg, right? Say, I want to kick off this job, it's going to run this binary with this arguments, it's going to need this much memory, it's going to need this much disk, all that kind of stuff. It's called Borg config. When I started playing with Yarn on Hadoop, I noticed it didn't have that. So I sat down and wrote a library that would basically be like Borg for Yarn. And I call it Kitten, because it's playing with Yarn, right? That's so cute. Anyway, kittens are great, aren't they? So if you want to get started just kind of messing around with Yarn, I wrote an example that uses Kitten. It's called branch reduce. So my graduate student, grad school, I was a operations research guy. So like branch and bound, integer optimization, combinatorial optimization. I love that stuff, all right? So branch and bound is a way of solving very large, very difficult optimization problems by basically exploring a tree where we make various assumptions about what the values of variables are, and we see how those assumptions kind of like lead to better objectives or lower objectives or whatever. Nonetheless, if you're interested in like playing with Kitten or trying out something like Yarn and you're looking for a non-trivial application that uses it, branch reduce is there for you. So just to give you a feel for like what it's like to use Yarn. And that, ladies and gentlemen, is it. And I'm like happy to answer questions for as long as you like, but I'm going to drink some more water first. Maybe a little bit more water first. Okay, questions? Really? I explained everything that? No, I didn't think so. Hi, how you doing?
Hi, yes. Can you tell me a little bit more about Seismic Hadoop?
So Seismic Hadoop is actually online as well. So it's up at like github.com/cloudera/Seismic Hadoop. Yeah, so go play, have fun. Yeah. Yes?
What are the differences between Impala and Hive?
Oh, sure. So Hive is really like an abstraction layer on top of MapReduce.
Right.
So when you write a Hive query, it maps it down to actual MapReduce jobs. Right? Impala doesn't do that. Impala has little Impala agents that run on all your data nodes in your Hadoop cluster. And they run all the time, continuously. They're written in C++. And there's no MapReduce. We don't ever do MapReduce jobs. It's all the optimization and aggregation and filtering is all done in Impala. Just as it would be as if you had like, you know, a big MPP database and you were like issuing a query to it. Okay. Yes?
So does it replace Hive, or does one thing that
Oh,
others use?
no, they play very nicely together, right? So Impala uses Hive's metastore to know like the schema of data and like know where data lives and where to read it. So the two can like basically coexist perfectly happily. Yeah, so it's not designed to be a Hive. You'll still do like there's still like batch processing jobs, like very large scale. If you know like ELT, like extract, load, and like you can still look at like your ELT queries as being primarily Hive queries, and then your interactive queries as being Impala queries. Okay.
Are there other tools that you can write and talk? You know, you like Tableau, the connectors. that
Yeah,
you can do
so since Impala uses the Hive metastore, and Impala gets plugged in right into Tableau, MicroStrategy, easy peasy. Yeah. Yes?
Yeah, with Hadoop, you still doing like batch type of analytic application, right? So,
Yes.
so if you really wanted to do these real-time sort of, you know,
Yeah.
analytics, what would you, add to it?
What would I add to my stack?
Yeah.
It would depend on what I was doing. It would probably be some combination of Storm and HBase, I think at this point. Yes, Storm and HBase. Like I think if we can find the Cerner talk, I'll try to like dig it up and then like link it to you because it's really good. It's just a really nice real world example of someone doing this, like not messing around. Yeah.
I've been reading that Nate Silverberg as well as
Yeah.
And I've been following his work on the 538 website. Now, I've also been following the other pollsters like Rasmussen.
Yeah.
And he was saying that the problem with his polling, which was
Terrible.
one of the worst.
It was awful. It's like 24th, right?
Yeah.
Yeah.
Right. The third from the bottom of
Yeah.
all the pollsters.
Yeah.
He said it was a data collection problem because it was phone banking or
Yeah.
phone calling, and that was probably the last polling that would be done by phone.
Let's hope so.
You're right,
Yeah.
and I was just wondering, sort of in your analysis, if you can figure out how technology plays into the polling. If you could see how that goes forward. If people are not using phones, or if they're using smartphones, or
Yeah.
they're using other types.
How does that work? So I mean, you're right. So I mean, I'm not an expert in this stuff, but I'm gonna try to sound like one for the next 45 seconds. So the NBCs and like the Marist, CBS Times, all those kinds of things, they actually like would be willing to call cell phone people, and Rasmussen reports did not. And if you don't call people who are cell phone only, right, if you're not going to be able to reach them, you're going to miss a ton of Obama voters because there's so many people less than 30 that are cell phone only, including me, because I'm older than 30, but nonetheless, right? So the problem with doing that is it's very expensive. And so like Rasmussen and Gallup and people who missed it badly can't afford to do that every day the way they can now with like the robocalls. So with respect to data collection, we're going to need some cheap way of figuring out what people are going to do, cheaper than calling up all these different cell phones, that has the same sort of statistical validity and all the good stuff we get from our more expensive models. And I think it's going to take a couple of election cycles before we figure out how to do that.
But Silver was just averaging all these different polls.
He was being a little more clever than that. So he actually like assigned weights based on like the lean of a particular pollster. So Rasmussen had a particularly conservative lean, public policy polling has a particularly liberal lean. So he's actually doing like smarter weighting than just a simple average.
So you don't see a way to kind of weight, old technology versus newer technology?
Oh, I'm sure we'll always be using hybrids. I just mean that like I agree that Rasmussen's probably going to go away as a source of data. And my concern is like the NBC, CBSs, they aren't done frequently enough because they're so expensive to really, like sort of fill the gap with respect to data. I mean, I could be wrong. Like, what the hell do I know, right? I'm a data scientist. I guess that's why I should know. You're right. Okay. More questions? Yeah, what's up, man?
Your vast travels around the world. Do you cross paths with IBM's Watson team at all?
I have never crossed paths with IBM's Watson team. I saw them once at a conference, and they saw me come in and kind of ran the other way. No, I'm kidding. No, I've never actually met them. If you know somebody, I'd love to talk to them. I think it would be fascinating. I'm a huge fan of their work. Yeah.
Yeah.
Actually, I feel bad because you've asked like 2 questions already. I'm sorry.
Yeah,
I'll
so,
come back, I promise. Yeah.
so for the data which is like in RDB and the system, and we want to process it using Hadoop, is there a way to actually get the data, like
Yeah.
stream it and
So there's a few different ways. So there's a tool Cloudera wrote many years ago called Scoop. It's not part of the ASF, the Apache Software Foundation as well. That it's basically kicks off a whole bunch of MapReduce jobs that are sort of smart about sucking data out of a relational database in parallel. And then Cloudera provides like connectors for Netezza, Teradata, Oracle for like doing fast data transfer using like their proprietary APIs.
but that's not streaming data, it actually makes a copy of the
It
data.
actually makes a copy of the data, right? So you want to do something like kind of clever involving like copying like write logs or something like that. That would actually be kind of fun. We should talk about that. But yeah. Yes.
Yeah, in regards to hardware, what do you think? What kind of ideas do you see, and what do you expect to see in 10 years to help all these, problems with MapReduce and all that? Like, what would you
Yeah.
like to see
What would I
from
like
a
to
hardware
see?
point of view?
Networking. I have like buddies because I'm ex-IBM, nothing. Who do like chip design stuff, and they're always asking me like, Josh, what do you need in terms of like chips for your Hadoop jobs? And I'm like, I need low power. Your chips from 4 years ago were amazing for the kind of stuff I do. Right? I'm IO bound. I just need low power. But what I really need, what I'd be willing to pay ridiculous amounts of money for, is super fast networking. Right? The 68 gigabits per second, whatever that stuff. Let's just keep going. let's not stop anytime soon. Yeah, that networking.